Welcome everyone, and in this video I'm going to discuss the relationship between the principal quantum number n and the angular momentum number denoted by small l. As I said initially that when dealing with the angular momentum number, the angular momentum number tells us about the shape of an orbital. N, the principal quantum number, tell us the kind of orbital we are dealing with. Which orbital? The orbital we are dealing with. So as chemists, we need to know the relationship between these two. And the relationship is very simple. That angular momentum number L must be less than or equal to the principal quantum number n minus 1. This is the relationship. And what does it mean? We're going to do analysis of that. Imagine a situation whereby when principal quantum number n is equal to 1. What does this one mean? When principal quantum number, the quantum number is equal to 1, if we follow the relationship where L is going to be n minus 1, so we are going to have 1 minus 1, so L is going to be 0. This means that the orbital in question here is S orbital. So in terms of electron arrangement, we are going to say we are dealing with a 1s orbital. Next, when the principal quantum number n is equal to 2. What does this one mean? Or what is the relationship? I'm going to follow the same relationship where L, which is the angular momentum number, must be equal to or less than 1, n minus 1, sorry. So the angular momentum number that I'm dealing with is going to be 2 minus 1, and therefore L is going to be 1. And we said when the angular momentum number is equal to 1, Here we are talking about the p orbital. And when we are talking about the p orbital, so we are going to have two situations. Here, therefore, L can be 0. At the same time, L can be 1. So when L is equal to 0, here we are referring to the s orbital. When the angular momentum number L is equal to 1, here we are referring to the p orbital. So in terms of electron arrangement, I'll simply say I'm referring to 2s and 2p. These are the orbitals that whenever the principal quantum number is 2, the angular momentum number can only be 0 or 1. Next, when principal quantum number is 3, so we're going to say when n is equal to 3. What is going to happen? I'm going to have a situation whereby L, so L 3 minus 1, therefore L is equal to 2. When it is 2, what is going to happen? Therefore, L can be 0, 1 or 2. And this corresponds to s orbital, p orbital, and d orbital. Lastly, when principal quantum number n is equal to 4, I'm going to do my arithmetic using the expression. And according to my expression, L can only be less than or equal to n minus 1. So if I do my arithmetic, I'm going to have L equal to 4 minus 1. So L is equal to 3. What does this correspond to? So it corresponds to a situation whereby I'm going to have L being equal to 0, L being 1, L can be 2, and L can be 3. So if that's the case, what does that one mean? It means that when L is equal to 0, I'm referring to the s orbital. When L is equal to 1, I'm referring to the p orbital. When L is equal to 2, I'm referring to the d orbital. When L is equal to 3, I'm referring to the f orbital. So when I'm writing the electronic configuration, I'm at liberty to say now I'm going to have because I'm dealing with the fourth orbital, so I'm going to have 4s, I'm going to have 4p, I'm going to have 4d, and I'm going to have 4f. So all these explains what can really happen. The same can also be told here because we are having 3, so meaning I'm going to have 3s, 3p, and 3d. I'm also going back. I already said that here we are having 2s and 2p. And lastly, here we are talking about 1s. So that's the major relationship between the principal quantum number that tells us about the number of shell we are talking about, or which shell are we referring to, and the angular momentum number, which tells us about the shape of that particular orbital that we are referring to. Thank you very much.